Hello everyone, and welcome to our SMO Open review session. Thanks for joining today, and I do suspect a few more people should be coming in the next few minutes. As you may have noticed, today's session is scheduled to start at 3 p.m., which is why you are here, instead of 3:30 for yesterday's SMO senior session. And this was planned before the SMO, but I kind of had the inkling that maybe 2.5 hours would not quite be enough for the SMO Open. Indeed, those of you who took it probably think, nope, 2.5 hours is definitely not enough. Questions were real difficult. It was a huge, painful nightmare. If that's what you thought, then you would understand why we might need a little more time. But this is meant to be quite relaxed, so please feel free to walk around, get a snack, get a drink, have a stretch every now and then, and even if you need to pause it for a while and you're a few minutes behind, that's okay, because as long as you have this link, you can always come back and watch anything that you need to catch up on later. Now, a few things before we get to the content proper. Firstly, about the chat. So if there's any issues with the video or the audio, if the stream starts lagging, if my internet cuts out, as happened in the SMO Junior stream 2 days ago, let me know. And if I make any serious mistake, please inform me in the chat so that everyone else is also aware. Now, especially for the SMO Open, that can happen because there are lots of questions and it is pretty long. So it can happen, and if I do something real silly, please let me know. If there's anything that is unclear, do ask and I will clarify if there is sufficient time. And also, if you think there is a much better method than what I'm suggesting, do say so. And the reason is because I did not get access to the questions until right after the SMO Open, so I looked at the questions basically last night because for those of you who joined me in the SMO Senior session yesterday, you know that we're doing that in the afternoon. So I was looking at the SMO Open questions last night, and so these are the solutions I think that will work. But hey, if you have something better, please share. Now, on the other hand, please don't spam the chat and please be polite. Now, I know that a lot of you are curious about scores and cutoffs. Maybe I will say something first. The paper was definitely more difficult this year. Right? So by difficult, it's difficult across the board, meaning that there are more difficult questions, and then the easy questions also are more difficult. So across the board, it's been shifted up. So I would anticipate that maybe the cutoffs might drop by a point or two, but I wouldn't say that is a certainty, or that all of the cutoffs will drop by 1 or 2. Maybe some cutoffs will drop by more, some of them may not change. I do not know. So if you want to discuss scores, you want to talk about cutoffs, and you want to talk about what I need to get into, let's say, the national team, what do I need to get, a silver, a gold, a bronze, honorable mention, whatever it may be, keep that to a minimum except during the breaks, so that we can focus on the problems which are difficult enough as it is. So our plan is very simple. I'm not going to go into the nitty-gritty details, especially for the SMO Open, right? If let's say that we get to a quadratic equation, I'll just say, okay, here are the solutions. I'm not going to go into every single nitty-gritty computation simply because there's no time. I want to focus more on how you would go about solving the problem and any insights that are useful, as well as any theorems that are important and perhaps some of you may not know. Now, you probably have heard this a lot from teachers over and over again. You must learn from your mistakes. Now, for the SMO, that's not quite so simple. And in fact, for math in general, it's not so simple to say, oh, let's learn from your mistakes. Because it depends on what exactly are you supposed to learn. Once you're at the SMO Open level, which I presume those of you who are watching this are either taking the SMO Open this year, next year, or you're at least interested in doing well. You need to be able to partition up your understanding of math instead of thinking of it as one huge homogeneous blob. There is the knowledge aspect where you need to learn more stuff. For example, you need to know your trigo identities, you need to know vectors, you need to know complex numbers. You need to know some modular arithmetic. You need to have these tools available to yourself, and this is the knowledge aspect. Now, if let's say that you looked at my review and then you say that, hey, I did not know that theorem at all. I've never, let's say, heard of Euler's theorem, for example. Then, of course, there was no way you could have solved the question and you don't have to feel bad. But now, if you know Euler's theorem, you have gained some knowledge. The next element is problem solving. So, if let's say that along the way, you see the solution and you realize, oh, I actually missed something. I didn't notice that these two numbers were related. I didn't notice that this was not just a coincidence, this was very deliberately chosen. Then that improves your intuition. So the problem solving is basically coming out with a plan. When you look at the question, what do I look out for? What should I do? Anything suspicious that stands out. And that is the problem solving aspect. Now that is a different thing from knowledge. You may actually know all the things that are required to solve the question, but you didn't manage to put them quite together. So drawing these linkages and all is something else that you want to consciously take note of. Was there any reason why you didn't consider such an idea? Think about it. And we are doing this review session right after the SMO Open yesterday because you still remember what went wrong for those questions that you didn't do, and you also probably remember what went right for those questions that you did manage to solve. Now the third part is execution, and execution meaning doing it after you have planned out what you will attempt for that problem. For example, you may say, I'm going to use Pythagoras' theorem. You may say that I am going to use properties of the circumcenter. You may say, I am going to use the binomial theorem. Now, whatever it is that you are doing, the execution part is where you make the careless mistakes that cause you to be very annoyed. Why did I actually write down 2 plus 2 equals to 6? Why did I go and square root 4 and get negative 2? Well, if that is the issue, that's execution. And that's an easier problem to fix. You just need to practice a bit more, and then these mistakes will slowly reduce. So there are different things that you should be looking out for. Firstly, anything that you didn't know. Second, any patterns and ideas that you can pick up. And thirdly, if there are these sort of silly mistakes, just try to avoid them. Now, some of you are hearing this for the third time, but just in case, you are joining only for the SMO Open session today. Let me introduce myself. My name is Wei, and I was from NUS High, and I just graduated from NUS with a double degree in math and computer science. So I do have some experience with these Olympiads as a student, plenty enough to be fair, because it was fun. I did math Olympiads because they were fun, and I think that has to be part of the important that's an important part of the experience of doing math Olympiads. You have to enjoy it, so that it isn't just a torture and it isn't just like trying to get one more mark every time. Right? It's about learning, enjoying all kinds of math. So I did well enough in the SMO for Junior Senior Open, but I didn't get into the IMO team at that time. To be fair, it was a very strong batch of students, but at least my reflection on it was that I didn't quite get the balance correct. When I did all of those practices, I didn't quite learn new things. So I built up my intuition, and I also was pretty good at executing correctly because I did lots of practice, but I didn't supplement the knowledge that I needed. So there were certain things that I thought, maybe I don't need to learn this, and so I didn't learn it, and it wasn't quite enough. So you see that for the SMO Open, there are some things that you really need to know. You need to know enough number theory, you need to know enough geometry, you need to know enough combinatorics that are outside of the usual A-level syllabus, even up to H3 or further math. And if you are interested to learn more, that's things that you have to develop on your own. So before we begin, just a couple of acknowledgements. You can see the 2 logos at the top. This is not an official Singapore Math Society session, so if I make any mistakes or if any of the solutions seem a bit too long and you think that, was the SMO problem setter really thinking of this method? Perhaps not. Hopefully along the way, I also have found one or two solutions that are a bit shorter than what the problem setters intended. And that is also from me. That was maybe not the original intent either. Now, these sessions are also supported by Math Hub, where I am currently teaching and where I'm actually physically located right now. So my thanks to them for giving me this time to conduct the session and for a little bit of technical resources and publicity. However, this is also not an official activity of the center. Yeah, and finally, thanks to Lim Lee and family for helping to publicize this session on their blog, which is presumably where quite a number of you came to know about this session. Okay, so it looks like we have got a slightly higher number. And in case any of you are watching back later, if you need to leave early, just a reminder that this will be recorded in full and it will be still on YouTube. So if you need to leave, let's say after an hour or two, just know that you can watch it back later. Alright, and now we're going to get into the fun stuff, which is the problems themselves. I have to say that among those of you who are watching, there are different priorities over here. Right? For those of you who are hoping to, let's say, get an honorable mention or a bronze, now, most of your points are probably going to come from the first page, which means that the next 45 minutes or so are probably the most important, because those are the questions which you would be most likely to be able to solve. Now, on the other hand, some of you here solve 15 questions and you're curious about the 10 most difficult questions. Now, those will probably come a bit later, but I would still encourage you to stay if you can. And the reason is that you need to bank in as much time as you can to get to those difficult questions so that you can explore them, you can experiment, and you can think about them. So you do need to solve the easier questions pretty fast if you want to get a better score. So perhaps from here you can see certain ways of getting to the solutions faster, even if you had solved the question during the SMO itself. Alright, so let's start with question 1. So you're given that beta is less than alpha, and they are in the interval from pi over 2 to 3 pi over 4. You are told cosine alpha minus beta and sine alpha plus beta. What you're asked to find is the absolute value of sine 2 alpha times 2021. Immediately, you should ask yourself, how do I get from the two given angles, the cosines and sines, to 2 alpha? Don't jump straight into expanding this using your compound angle formulas. So if you pay attention to alpha minus beta and alpha plus beta, there are already so many trigo identities you can use. You might think of sum to product, you may think of compound angles. But the one thing that would stand out to me is that 2 alpha is actually alpha minus beta plus alpha plus beta. Meaning that what they're asking you for is sine of the sum of these two angles. Now I'm going to do a substitution to bring this into focus. You can call this alpha minus beta x and alpha plus beta y. And then your 2 alpha becomes x plus y. Notice that once you have done that, you are more or less back to the usual question that may well appear even in an SMO senior. Now, the first thing to remind ourselves is that alpha minus beta, which is x, is in the first quadrant, whereas alpha plus beta would be between pi and 3 pi over 2, so it's in the third quadrant. And this is just important when we have to deal with positives and negatives. Okay, so let's just write down the details here. So cos x equals to 12 over 13 in the first quadrant means that sine x is 5 over 13. This is your 5, 12, 13 triangle. And likewise, if sine y equals to negative 3/5, and you're in the third quadrant, then cosine y is negative 4/5. This is a 3, 4, 5 triangle, but it is negative in the third quadrant. Therefore, you want sine x plus y. That would just be sine x cosine y, then plus cos x sine y. So do the calculation carefully. And this is one of those annoying calculations where if you get it wrong, you'll be quite annoyed. And you would say, shouldn't have lost that 1 mark. So please, when you see such questions, bear in mind, the only difficulty is getting the calculations correct. Don't mess them up. So this would be negative 56 over 65. You have to do a little of the computations by multiplying by 2021, but essentially we are there. So just compute correctly and get your answer 1741. Question 2. Find the number of solutions of the equation modulus x minus 3 plus modulus x minus 5 equals to 2. Okay, so this is quite a generous question too. It should already be pretty clear by inspection that 3 and 5 have a difference of 2. So you can normally split into cases and track. I will just mention that case, which is that if x is in the range from 3 to 5, then the left hand side is x minus 3 plus 5 minus x equals to 2. In other words, anything in this interval is a solution, so you don't need to look anywhere else. Right, so that gives you infinitely many solutions. And your answer is 99999. Question 3. Evaluate 1 times 2 times 3 plus 2 times 3 times 4 plus 3 times 4 times 5 summed up all the way to 10 times 11 times 12. I'm willing to guess that at least a few of you here did this by manually multiplying everything and adding them up. And to be honest, if you see such questions in the SMO, maybe not this one, but something else that can be manually computed, it's probably worth to manually compute if you can't think of a better way. Since looking at such a problem as this, you don't really have too many options if you haven't seen the idea before. Now I'll show 2 different methods of doing this, one using a telescoping sum and the other just using your standard summations. So the first way you could have done this is possibly the more standard way, which is to write it as a summation of n minus 1 times n plus 1. Now take note that I deliberately used n minus 1 n plus 1 instead of n plus 1 n plus 2 because this would be easier to expand. It gives you n cubed minus n, and that is easier to sum up. Now this sum goes from 2 to 11, but actually for n equals to 1, this is equal to 0. So to make my life a little easier, I'm just going to make it to sum from 1, because that's like adding nothing. Okay, so with this sum, then it becomes the sum of n cubed minus n, and n cubed minus n, you can sum n cubed, which is 11 times 12 over 2 squared, minus the sum from 1 to 11, which is 11 times 12 over 2. So if you do this and compute carefully, numerical answer is 4290. So that's the first approach. Now, an alternative approach is using telescoping sums or method of difference, if that's how you have heard it recently. Now, how the method of difference for this sort of sum can be done is as follows. If you have 1 times 2 times 3, you can basically stick something at the front and back. Oops, okay. And each of these would then become a difference. So 1 times 2 times 3 times 4 minus 0 times 1 times 2 times 3. The next one would be 2 times 3 times 4 times 5 minus 1 times 2 times 3 times 4, and so on. And I guess the attractive part of this method is that if now you had to multiply together 5 numbers or 6 numbers and add them up, this approach will still work, except that we adapt it by using a different fraction and a different pair of differences. So likewise, 10 times 11 times 12 is 1/4 times 10, 11, 12, 13 minus 9, 10, 11, 12. So you sum up everything on the right hand sides. You get your very satisfying cancellation, with the only term that's being left over as 1/4 times 10 times 11 times 12 times 13. So this would also give you the same numerical answer at the end of 4290. Right, so just a couple of ways in which you could have done question 3. Okay, next up, question 4. It is given that the solution of the inequality, square root of 81 minus x to the power of 4 less than or equals to kx plus 1, is a less than or equals to x less than or equal to b, with b minus a equals to 2, where k is positive. Determine the floor of k. First thing you may think of is, can I square this? In your mind, if you think of squaring this, you realize that that's not going to work out, because you've got x to the power of 4 and then a quadratic on the right hand side, so that's a quartic. So squaring it, probably not such a good idea. Now, we don't actually know what's k, so that is not helpful if we want to do a factorization approach or if we want to use any identities. But we do know that k is greater than 0. So let's look at that and see what it could tell us. Now, if they tell you that the solution of the inequality is between a and b, and this is the entire solution set, we can try to look for a solution. So look for any solution. And that will give you an idea of where to go. Now, for the left-hand side to be defined, it means that 81 minus x to the power of 4 has to be non-negative. And for it to be non-negative, x must be in the range from minus 3 to 3. Now, this is not the solution set, this is just the set of values such that the left-hand side is even defined. But actually, that already tells you a way to look for the solution. If you let x equals to 3, the left-hand side is 0, and the right-hand side is definitely positive, because k is greater than 0, so the right-hand side is at least 1. So that means that 3 is a solution. Now, if 3 is a solution, and definitely you can't get any solution more than 3 because the domain is minus 3 to 3, it means that for you to have an interval of length 2, it must be none other than 1 to 3. So this is an interval of length 2, which contains 3, and must be within minus 3 to 3. So the only way that this could happen is that A is 1 and B is 3. If the range is from 1 to 3, that means that 1 must be the equality case of your inequality. This must be the equality case. And so if you want to find k, you can just substitute in 1 to find out what is k. If some of you are wondering, how do you know for sure that's the equality case? Well, the function on the left is a decreasing one, and the function on the right is an increasing one. So if you want to get the interval, it would definitely be over here, and so therefore at x equals to 1, it must be equality. Okay, so substitute in square root 80 equals to k plus 1, and so that would give you the value of k as square root 80 minus 1. Square root 80 is slightly less than 9, and so therefore the floor of k is just 7. Okay, question 5. Figure below shows a cross that is cut out from a 10 by 9 rectangular board. Find the total number of rectangles in the above figure. Note that a square is a rectangle. Okay. Now to solve this, alluding to what I mentioned earlier, you probably need to know two things. You need to know how to count actually any number of rectangles from a nice rectangular board without this weird shape being cut out. So you need to be able to count rectangles. Now in general, if let's say that you have a by b rectangle as your grid, and you want to find out how many rectangles there are inside. Now, in order to draw a rectangle, the rectangle has a couple of very basic features. A rectangle has 2 horizontal and 2 vertical lines. Right? 2 horizontal and 2 vertical lines give you a rectangle. So if you have an A by B rectangle, that means that you have got A plus 1 horizontal and you have got B plus 1 vertical lines, and there's a 1-to-1 bijection between the rectangles and picking 2 horizontal and 2 vertical lines. In other words, if you wanted to count the number of rectangles, it would be A plus 1 choose 2 times B plus 1 choose 2. So you probably need to do this, at least, if you hope to solve a question like this. You need to know how to do it for a simple rectangle. So that's the knowledge part. And now how we proceed is to apply that to our strange looking cross shape. Now our cross shape is cut out from a 10 by 9 rectangular board, and now it kind of has 2 overlapping rectangles. Right? So there's this, okay, I can't draw a very straight line, excuse me for that. There's this rectangle over here, and there's another rectangle over here. So we can just count the number of rectangles within each of these two outlined rectangles first, and then we can subtract off the ones that we double counted by PIE. The ones that we double counted are in the overlapping rectangle over here. So that's what we need to subtract off. Okay. So firstly, the green one is 6 by 10. So with 6 by 10, then the number of rectangles is 7 choose 2 times 11 choose 2. For the purple rectangle, that is 4 by 9. So for 4 by 9 rectangle, the number of smaller rectangles is 5 choose 2 times 10 choose 2. Finally, for the blue rectangle, that is 4 by 6, the overlap. So it gives us 5 choose 2 times 7 choose 2 rectangles. So it just remains for us to do the calculations, and this is where we get to the execution phase. Just make sure that you compute all this correctly. So this is, let me just write down the values. 21 times 55. This is 10 times 45. And this is 10 times 21. So you add the first two and subtract the third to get your answer, which is 1395. Okay, next up is question 6. Consider all the polynomials p of xy in two variables such that p of 0, 0 equals to 20, 20, and for all x and y, pxy equals to px plus y, y minus x. Find the largest possible value of p11. Okay, I'm going to give you the SMO solution, which is basically an euphemism for the way to get your numerical answer, and then after that I will try to give a more rigorous proof for why that particular answer is really correct. So first of all, it says consider all the polynomials p, x, y in two variables. We don't really know much about two variable polynomials in terms of properties. At least when I say we don't really know much, meaning there hasn't really been much in the syllabus that most of you have learned. So we don't really know too much, except that it's some power of x times power of y times some constant plus another power of x times another power of y times a constant, and you have some number of these terms that are added up. That's your polynomial, and somehow at 0, 0 it is 20, 20. Now we can start by actually taking away 20, 20 though, and I'll just come up with an auxiliary polynomial. Let q of xy be p of xy minus 20, 20. So I just shift it downwards by 20, 20. Now of course this new polynomial will still satisfy the same things. Right? So q of 0, 0 is now 0. And q of xy will still be q of x plus y, y minus x, because all I did was subtract 20, 20 from the definition of the polynomial. Now here is the cheating approach to solving this, which assumes that they mention largest possible value. Right? So since the maximum exists, you can exploit this to observe something. Now suppose that Q is a solution, right? So suppose you have found some polynomial. So let Q be a solution. That means a valid polynomial such that you got some value of Q11 that is more than 0. Now if Q is a solution, this polynomial, then I can multiply Q by anything I like and it would still be a solution, right? So then a constant times Q would also be a solution. So you could, let's say, multiply the polynomial by 100 million and that would still be a solution. And of course, if you make C very big, then your Q11 can go to infinity. Right, so I should say C times Q11 can go to infinity for your choice of Q. Yeah, so because of that, hey, wait a second, that doesn't make any sense because there is a 5-digit limit in the SMO answer, which means that you can't even find such a solution Q, and the only way that this can happen is that Q must be 0, the 0 polynomial. Okay, so that means that the only way that this can happen is that Q of every value must be 0, otherwise you can get something like that. Okay, I should say technically we don't know Q is a 0 polynomial. From here we can just conclude that Q11 will be 0. So maybe that's a more precise way to write it. Q11 must be 0 because my argument only applies for 1, 1. Okay, so if Q11 is 0, then remember P is 2020 because it's 2020 more than that. So this is a slightly cheap approach. Let's go with a more rigorous approach to this. And I'm going to use an idea of monovariance in order to justify this. Now you see that, okay, so a proper solution now if any of you have alternative suggestions after this, again, feel free to share. Right, so my proper solution is I realized that you can actually do some back substitutions. Right, so now it tells you that P of xy is equal to P of x plus y, y minus x. Now let's try to make the right hand side into 1, 1. Now how would that happen? Well, if that is 1, 1, it means that x is 0 and y is 1. So that means that I have concluded that P11 equals to P of 0, 1. Now let's now try to make this 0, 1. This time it would give you x is minus half and y is half. Let's try to do that one more time, and then I'm going to explain where I'm going with this. So we have this time, y is going to be 0, and then x is going to be negative half. Okay, I think we'll do one more step of this. And so if you repeat this one more time, this would give you x is negative 1/4 and y is negative 1/4. So basically from p11 we have backtracked down to p of negative 1/4, negative 1/4. Now you notice that we have basically backtracked a few times. You could go and solve it in general, but I'm using the specific example to make it easier to see. And if you repeat this a few more times again, you're going to times negative 1/4 again. Means that after a few repetitions, you'll get 1 over 16, 1 over 16. And this pair is going to converge to 0, 0 if you keep repeating this. Now if it converges to 0, 0, then because your polynomials are continuous, it means that by getting closer and closer to 0, 0, your value will get closer and closer to 2020, and eventually it must actually be equal to 2020. And here I'm using the fact that polynomials are continuous, which technically, I'm not sure how much you're supposed to be able to quote continuity, but since calculus is in the SMO, I think that's fair game. Now I would further add that this actually works for any xy, apart from 1, 1, because as you repeat this operation, you realize that the distance of your points to the origin is reducing. It's a monovariate, it halves every time. The sum of squares halves every time. So if you were to apply this to any other value, if they ask for p of 2090, you could do the same thing as well. So this would be the so-called proper justification. Why is it can only be 0? Sorry, q can only be 0 and p can only be 2020 at 1, 1. Okay, question 7. So a few of you probably already are either getting ready to laugh or to get really, really angry. So this question, in your usual 3D Cartesian space, I, J, K are your usual vectors. There's a line and there's a plane. And they intersect at the point ABC, and you're asked to find the value of A plus B plus C. Now, this question does serve a good purpose, however, which is that sometimes you have to just pause a while and look at the question and think. Now, we are pretty excited to jump into every problem that we see because, well, that's what we do for exams, for competitions, and for most of our encounters with math. We look at the question and we do the first thing that comes to mind. But before we start doing a whole lot of intersections and then solve this and solve that, hold on a second and pay attention to what's happening here. So I didn't notice this the first time I saw the question because I was bumping along somewhere in the MRT, and then I looked at vectors. I'm like, no, I'm not going to do a vectors question on a tiny screen on my phone. Let me skip on to the next question. And then when I finally sat down and read the question again, I realized that, oh yeah, there is a pretty cheap gimmick here, which is that ABC is on that plane. So if it's on the plane capital pi, that means it satisfies the equation, and that means A plus B plus C is 16, and you don't need to know the intersection at all. So if anything, I'm just glad for the presence of this question because it saves me a bit of time since there are lots of other time-consuming questions later on. Okay, I think we will go until question 10, then we'll take a short break. So question 8, find the minimum value of x plus 7 squared plus y plus 2 squared subject to the constraint x minus 5 squared plus y minus 7 squared equals to 4. This immediately, you should know, is the equation of a circle. The center is 5, 7. And the radius is 2. Now this other side, x plus 7 squared plus y plus 2 squared, is also an equation that, an expression that looks like it came from the equation of a circle. But actually, we know that the equation of a circle is just the distance formula squared, right? Since the equation of a circle just tells you all the points which are a distance r away from the center. So this here is actually the square of the distance from xy to the point minus 7 minus 2. So I'm just going to write the distance to minus 7 minus 2. In other words, what you're trying to find is a point on the circle that is as close as possible to minus 7 minus 2. So let's draw this roughly. You have got 5, 7 somewhere here. You've got a small circle of radius 2, and then you have got some minus 7 minus 2 over here. So minus 7 minus 2, and then this is 5, 7. Now you want to find a point on the circle that is as close as possible to here. It is fairly obvious that you should draw a line connecting them. And after you draw a line connecting them, you pick the point down here. Now technically you could prove this using the triangle inequality, but I think it is fairly intuitive that you would just pick the one that gets you as close as possible in that direction. So all we need to do is find the total distance between these 2 points. The distance turns out to be root of 12 squared plus 9 squared, which is 15. And then you subtract off the radius. So 15 minus 2 equals to 13. Now notice that I didn't actually go and find xy. You could have found xy if you just looked at the gradient and then moved downwards in the direction by a length of 2. That would certainly have been possible, but it is not really necessary since we just wanted to find the distance. Yes, I forgot to square it, right? 13 is the distance, but it's the distance squared. So I shouldn't underline that as the answer. That is just one step away. So the minimum is 13 squared equals to 169. Once again, it's about recognizing these patterns, right? By patterns, I don't mean number patterns all the time. Patterns meaning that this is an equation of a circle, this is a distance formula. So you recognize that this is not just an algebra problem, this has a geometric interpretation. Not every algebraic problem has a geometric interpretation, but some of them do. And you want to be able to pick that up as quickly as possible. Now, after this first page, we are starting to get into the more meaty section, which essentially means that if you guys are pretty new to the SMO Open and you're hoping to get an honorable mention or a bronze, your focus would mostly be on the first page. But don't dump out everything after that, because there are a few relatively easier questions scattered among the rest of it, even though the difficulty is slightly higher on average. Question 9. Find the largest possible value of alpha to the 4 plus beta to the 4 plus gamma to the 4 among all possible sets of numbers alpha, beta, and gamma that satisfy these equations. There's one thing which I want to say here, which is quite important, and that is for any one of you who isn't really very experienced as a problem solver or as a SMO participant. It's pretty difficult to make your answers integers. Meaning that if these values are chosen at random, it is quite difficult to make sure that your final answer is an integer unless they are chosen very specifically. Now there are 3 equations and 3 variables, so you probably suspect there aren't that many ways to do this. And as it turns out, if I told you that the sum of 3 cubes is 20, you might think of how am I going to get 20, and you can maybe guess that it is 27 minus 8 plus 1. In other words, your 3 values are 3 minus 2 and 1. Now I'm saying this right now because I literally just noticed this about 10 seconds ago before explaining it, and that's the sort of intuition you hope to develop. You look at the numbers and say, that's quite small, and even furthermore so for the sum of squares being 14. Right? This is 9 plus 4 plus 1. There are not many ways to do this, so you can actually get that sort of suspicion that maybe alpha, beta, and gamma are actually quite nice. And in fact, these 3 values would give you the correct answer of 98 already. Now, let me get to the proper solution to this problem. Alpha, beta, and gamma are most commonly seen as roots of equations, right? I think by now you have actually used that most often when you have solutions to a cubic. So we're going to try to make this into the typical Vieta's formulas. So you want to use Vieta's in a way. But when you want to use Vieta's in a reverse fashion, it means that you need to find the 3 things that are involved in Vieta's formulas for cubic. The first one's already there, right? The first equation is the sum of what would be your roots. Now the other one, which is the pairwise sum, you can do it using the first 2 equations. So you take the square of the first one minus the sum of squares this would be 4 minus 14, which is negative 10, and that would be 2 times of alpha beta plus alpha gamma plus beta gamma. So that tells you the second thing in Vieta's, which is that alpha beta plus alpha gamma plus beta gamma is negative 5. Now the next thing is you need to use another identity to extract out alpha, beta, gamma. And the identity I'm going to use is something that's pretty common in Math Olympiads because you do need a way of dealing with cubic expressions quite often. And it is this identity that if you take the sum of cubes minus 3 times of the product, one of the factors is going to be the sum, and the other factors would be alpha squared plus beta squared minus gamma squared, plus gamma squared minus alpha beta minus alpha gamma minus beta gamma. Incidentally, the left-hand side of this kind of looks like AMGM, and it can be used to prove the 3-variable case of AMGM. Now anyway, we have got all the values that we need in between. The sum of cubes is 20. The sum of roots is 2. The sum of squares is 14. And minus negative 5 is 5. So if you solve all of this, the next thing that we get is that alpha, beta, gamma is equal to negative 6. Right? So this is the thing that we can solve. Now that allows us to say that alpha, beta, and gamma are roots of the following equation. So the sum of roots is 2, so minus 2x squared. The pairwise product, the sum of pairwise products is minus 5, so minus 5x. And the product of roots is minus 6, so you get plus 6 equals to 0. Okay, so let's continue in a fresh page. So alpha, beta, gamma are roots of this equation. Oops, okay, this is... And you want to find the sum of the fourth powers. So here's how we do this, and this is a general method that works. Once you know vietas, you can actually use the fact that they are roots to reduce it down to a small enough degree, and then hopefully the vietas formulas will take the rest of it from there. So what we can do is to say that if alpha, beta, and gamma are roots of this, you can multiply throughout by x. And shift it over. And what this means is that alpha, beta, gamma are still roots of this new equation that we have written down. That means that alpha, beta, and gamma are going to satisfy this. You can write it in this way. So I sum over alpha, beta, and gamma. It's going to be the sum. So this is true for alpha, beta, and gamma. So I'm just going to substitute them all in and add it together. And so this would be equals to 2 times of the sum of cubes. Now let me refer to my paper as to what those values are. This is equals to 2 times 20 plus 5 times the sum of squares, 5 times 14, minus 6 times the sum of roots. So this would give you 98 as your numerical answer. Okay, finally, we'll look at question 10, which is pretty nasty. If P is the product of all the non-zero real roots of the equation, 9th root of x to the 7 plus 30x to the 5 equals to the 7th root of x to the 9 minus 30x to the power of 5, find the floor of the absolute value of P. For the more difficult questions, you are going to have to notice many different ideas. Why I say you have to notice many different ideas is that it will turn out half of them were not actually needed in the solution. But you wouldn't know which one, so you need to make as many observations as you can in order to make progress. So let me note down observations. Now firstly, I would notice that the 30 repeated itself. Is that important? Don't know, maybe. The next thing that I would notice is that all the powers and the roots are all odd. Now what does this mean? Well, if all powers are odd, it means that if I were to replace x by negative x, everything will get negated. Which means that if x is a root, then negative x will also be a root. Pity they didn't ask you for the sum of roots, right? They asked you for the product. Otherwise, this would immediately kill the question and the answer is 0. But they asked you for the product. Now, the next thing you could do is to ask yourself in reverse, is there anything I can do with product by doing some sort of reciprocal idea? So, any pairing ideas? And probably don't see anything. At least for me, I didn't see any way of pairing up roots apart from positive and negative. There's no way of saying that if, let's say, x is a root, then 2 over x is also a root. At least I couldn't think of something like that works, so nope, this seems to not work out. The next thing that I'll look at is non-zero. So I'll ask myself, is there anything I can do with non-zero? Well, 0 is obviously a root. But non-zero gives me the idea that, I can divide both sides by x without any problem because I'm not going to lose any non-zero real roots. But dividing both sides by x would at least make my expression look a little bit more sane. It doesn't give me this x to the 7 plus 30x to the 5, and what is all of this? So I'm going to divide both sides by x. First. And we'll see whether this works out. Now what I'm writing down here is my thought process, and so some of them worked, some of them did not work, and that's how math problems are like, right? It's not that you think of one approach, oops, that didn't work, oh no, this question is too hard, I give up. So if we divide both sides by x, it means that you are dividing by x to the 9 for the first root, and you're dividing by x to the 7 for the other root, because there's a 9th root and a 7th root. So what we get is the 9th root of x to the negative 2 plus 30x to the negative 4. And for the right hand side, it will become x squared minus 30x to the negative 2. Now all of the powers are even again. It's still 2, 4, 2 and minus 2. So I'm going to do another substitution to make this a bit simpler. I will let y equals to x squared. You see, all of this is trying to make it simpler and simpler until I feel ready to either make some observation, to solve the whole question, or to otherwise find something interesting about the product. So with this new substitution, x to the minus 2 now becomes 1 over y. 30x to the minus 4 becomes y to the minus 2, so 30 over y squared. And for x squared, it's just y. This would be 30 over y. Now we notice that when we get to this point, y is positive, right? And when y is positive, there's something interesting about both of these expressions. 1 over y and 30 over y squared, if you sum them up, this is decreasing. Whereas y minus 30 over y is increasing. So you have got a decreasing function on the left and an increasing function on the right, which means that there is at most one real root. And this is actually similar to question 4 earlier on, where we had one increasing and one decreasing, then it was an inequality. Now we know that there is at most one real root. Now when I say at most one real root, I mean at most one real root for y, because after you get y, then the x could be plus or minus the square root. Remember that the positive and negative still apply. So we're just dealing with y first, then after that we'll put the square root in later. Now whenever there is something of this sort where it says at most one real root, this is kind of an invitation for you to try to guess that root. And you're not guessing blindly, because you know that as you adjust your y, one side is getting smaller and the other side is getting bigger, right? So you will know how close you're getting, and hopefully, if the question is to be reasonable, you can find that one real root. At the same time, another thing that could be fairly said is, it is really unlikely for a ninth root and a seventh root to be the same, meaning that what's in the left hand side and what's in the right hand side are both supposed to be ninth powers and seventh powers in some sense, which does sound a little bit difficult to accomplish because the smallest ninth power is already pretty big. So intuition tells you that maybe I should either make both of them 0 or both of them 1. That's the easier way to look for this one real root. And so by inspection, you can see that it's possible for both of them to be 1, and that is when y equals to 6. When y equals to 6, then both of the expressions inside are 1. So therefore, if y equals to 6 works, then your real roots are x equals to plus or minus square root 6, and therefore your product is minus 6. And you put the absolute value, you put the floor, your answer is equal to 6. Okay, so thanks to everyone who has joined so far and is sticking around. Bit of self-advertising. Please like this video and subscribe to this channel if you're interested. This is the last review session for the SMO, but at the same time, I do hope to put up some more interesting content, and hopefully it's useful for everyone. So just do help out in that small way. And we're also going to move to a short break for about 5 minutes. So after that break, then we will get to maybe the next 7 or 8 problems. Yeah, so at this time, if you have any questions, or if you just want to discuss some stuff in the chat about scores, cutoffs and whatever, now would be a time that you can do that. Okay, and we are back. Remember, if you need to take a slightly longer break, just do feel free to pause it, and if you're a few minutes behind, it's okay. As you can see, our chat is pretty quiet. That's okay, the session is still useful, I would assume. If there's any questions that you don't get to ask during this period, you can always leave it in the comments after the stream is over. Okay, so don't worry if you didn't manage to get a question in because it was a bit delayed. Right. We'll pick up from question 11. It's a nice and relatively easy way to transition back in. So question 11 is the sum of a convergent geometric series with first term 1 is S. Now, if the third term of the series is the arithmetic mean of the first two terms, find the floor of 3S plus 4. First thing to say is that the geometric progressions, arithmetic progressions questions usually are the easier kind because that comes from the A-level syllabus. So this is one of those few questions that you can just do it in the most predictable way and it should work out. At least there's nothing else we know about a geometric series than its definition, so nothing more to do. Okay, so the third term of the series is the arithmetic mean of the first two terms. So let's write it as AR, and AR squared. And if it's the arithmetic mean, it means that AR squared equals to A plus AR over 2. In fact, the first term's 1, right? Oh, that makes things even better. It's just 1. Sorry, no need A. Okay, let's... I forgot that it was just the first term. So R squared is 1 plus R over 2. And this is a quadratic. 2R squared minus R minus 1 equals to 0. And it factorizes almost immediately. So R is minus half. And so S is just 1 over 1 minus the common ratio, which is 2/3. And then the floor of 3S plus 4 equals to 6. This is yet another reminder that the questions do not really go in order of difficulty. There is no way in which question 10 is easier to do than question 11. But that's why you should look at everything, just in case. Question 12. Now, if you took the SMO senior, you would know that a rather similar looking question appeared with sine A minus sine B and cosine A minus cosine B. This one is something similar to that as well. So you're given that sine A plus sine B is 1 over 10 and cosine A plus cosine B is 1 over 9, and you're asked to find tangent squared alpha and beta, right? Tangent squared alpha plus beta flawed. I'm going to use the same approach as I used in the SMO senior stream for the corresponding question. I think it was question 7 in the SMO senior, right? Which is to do a sum to product for both of them. And you do sum to product for both of them with the knowledge that sine of alpha plus beta over 2 and cosine of alpha plus beta over 2 are going to show up. And because they show up, then you can use the double angle formula if you need to climb back up to alpha plus beta. Okay, so let's use the sum to product. The first one would be alpha plus beta over 2, sine of it, then cosine of alpha minus beta over 2 equals 1 over 10. The other one would be 2 cosine alpha plus beta over 2 cosine alpha minus beta over 2 equals to 1 over 9. Now from this, you hope to get tangent squared of alpha plus beta. But unlike the one that we did the other day for SMO Junior, SMO Senior, this one is even easier. You can just take the equations and divide them. You can divide them because you know that obviously cosine can't be 0, otherwise both these equations would have turned out to be 0. So you can just do division. If you divide, you get immediately tangent of alpha plus beta over 2 is equal to 9 over 10. Then you can use the tangent double angle formula to get tangent of alpha plus beta. And tangent of alpha plus beta would be 2 times of 9 over 10 over 1 minus 9 over 10 squared. Now do remember that for your double angle identity for tangent is tangent to theta is 2 tangent theta over 1 minus tangent squared theta, which is what I'm applying here. So this would simplify after a little bit of work to 180 over 19. So now we have to square it and floor it. Again, I'm not going to get into the computational details. Just do it carefully, which I'm sure some of you must have had rather painful experiences squaring it and flooring it. But if you do it correctly, you get 89. And just like question 1, I don't really want to talk too much about computational shortcuts because unless something really obvious comes to mind, I think it only gives you minor benefits. Okay, next up, question 13. So we have kind of gone through another 3 so-called easier questions after the pretty difficult intermediate stage of questions 9 and 10. So 11, 12 and 13 are not so bad again. So determine the number of positive integers that are divisible by 2021 and has exactly 2021 divisors. Divisible by 2021, if you have taken the junior or senior or in fact any SMO in the past, you know that the year number is pretty important. So this factorization is 43 times 47. Incidentally, 2021 is 45 squared minus 2 squared, which is where these two big prime numbers come from. And your number has exactly 2021 divisors. Now to solve this, you need to know how to count the number of divisors of an integer. And so this I will just mention very briefly. Ironically, this was something in a junior question not too long ago. So given a prime factorization, and let's just write it as p1 to the alpha 1, p2 to the alpha 2, until pk to the alpha k. Now the number of positive divisors, factors, is alpha 1 plus 1, alpha 2 plus 1, and so on until alpha k plus 1. Now the reason for this is actually pretty simple. If you just think about where your factors come from, each of these factors would be p1 to the power of something, p2 to the power of something, all the way to pk to the power of something. And for the power of p1, you have got alpha 1 plus 1 choices. For the power on p2, you have got alpha 2 plus 1 choices, and so on. So you just take the product of them. What's the implication here? The implication is that if you have exactly 2021 divisors, and 2021 is 43 times 47, either your prime factorization looks like p to the power of 42 times q to the power of 46 for some prime numbers p and q, or it is just some prime number to the power of 2020. However, you also remember that it needs to be divisible by 2021. So it needs these two prime numbers. So if it needs these two prime numbers, then it cannot be a prime number to the power of 2020 because that's only one prime. So this one is out of the question. And for the first case, we really only have two choices. PQ can either be 43, 47, or the other way around. And we can't introduce any other prime numbers already. So there are only two ways. And we get to another relatively difficult question, because this is quite an unusual sum that you're asked to find. You're asked to find the sum basically of 100 choose 0 plus 100 choose 4 plus 100 choose 8 and so on up till 100 choose 100. So you're asked to find this rather strange looking thing. Probably it's because S is quite big and has some big power of 2, you want to get rid of it. I'm fairly sure there is some combinatorial interpretation of the sum of 100 choose 4k that can be counted easily, meaning that, of course, it is the sum of the number of ways to pick a multiple of 4 items out of 100, but I don't know how to count that any more easily than the original thing. So, I mean, there may be some easier combinatorial formulation, and please feel free to share in the chat if you are aware of such a formulation. However, I think there's an interesting method that came to mind, and I would like to share it. Now, the intuition comes from how did we get the identity if, let's say, it was just the sum from k equals to 0 to 100 of 100 choose k. Now, this is a common problem solving strategy. You look at what they ask you for, and you ask yourself if there is something slightly easier than that problem that you have solved before, or that you can at least try to solve. Now, if you're already aware of this, you might know that this is 2 to the power of k, and there is a combinatorial interpretation. But actually, you can also get this sum from the binomial theorem. If you expand out 1 plus 1 to the power of 100, this is precisely what you're going to get from the binomial theorem. Now, however, the issue is that this is 4k. So let's now take another step. What happens if I want to get all the even values? Okay, so this is 2 to the power of 100. What happens if you want to only extract out 100 choose 0 plus 100 choose 2 plus 100 choose 4 and so on? Now I'm going to write the general form here so that we can look at it and decide what to substitute. Meaning that the way to generate all of these 100 choose something is if you have 1 plus x to the power 100 is going to be 100 choose 0 plus 100 choose 1x plus 100 choose 2x squared plus 100 choose 3x cubed and so on until 100 choose 100 x to the power 100. So substituting x equals to 1 gives you the thing on the left. If you only wanted the even powers, so the even binomial coefficients, what you can do is to substitute in x equals to minus 1. Now x equals to minus 1, it would tell you that 0 equals to 100 choose 0 minus 100 choose 1 plus 100 choose 2 minus 100 choose 3 and so on until 100 choose 100. So if you substituted in x equals to minus 1 and you wanted to combine it with the first one, you could just add the two of them together and multiply by half. So it's the average of this one and this one. Sorry, plus 0 actually, which is 2 to the power of 99. Now the answer here doesn't correspond to, oh, so that means that here this thing on the left is 2 to the power of 98 and so s is 0. I mean, that is not actually going to be correct. But now, how do we extend it from here to here? Now, you want to be able to cancel off not just the odd terms, but you want to cancel off the 2 mod 4 terms. In other words, you need to select an x such that only the 0 mod 4 terms are fine, but the 2 mod 4 terms are going to get swapped around. So here's what we can do. We can substitute in x equals to I and x equals to minus I. You notice there were no complex number questions around. So you can substitute in I and minus I. Now your right hand side now would look like 100 choose 0 plus 100 choose 1 times I minus 100 choose 2 because I squared is negative 1 minus 100 choose 3I, and then we continue from there. Meanwhile, if you substitute in minus I, you get 100 choose 0 minus 100 choose 1I minus 100 choose 2 and then plus 100 choose 3I and so on. So that means that if you add up the cases for x equals to 1, x equals to minus 1, x equals to I, and x equals to minus I, you're going to cancel off everything except for these ones that you want in S. Now I'll leave you to work out the details because I think this is best done on a huge piece of paper if you have not seen it before. But our conclusion is that through these substitutions, it is going to be 1/4 of 2 to the 100, that's for 1, plus 0, that's for minus 1, 1 plus I to the 100, and 1 minus I to the power 100. Now you see that the minus 2 to the power of 98 now makes sense, because the 2 to the power of 98 is cancelling off the one at the front, 1/4 of 2 to the power of 100. So that means that S would just be 1/4 of the last two. One plus I to the 100 and 1 minus I to the 100. You can go and do all the exponential form stuff if you need to convert it. However, I would just prefer to say that 1 plus I squared is 2I to the 50 and then minus 2I to the 50. If you square both of them again, 2i squared is negative 4, and negative 2i squared is also negative 4. So it's 2 times negative 4 to the power of 25. And if you just work out the indices carefully, take the absolute value and divide, your answer would be 2, which is actually this spare factor over here. I'm not too sure if there is a way to do this that does not involve complex numbers, but I think this is actually a good thing to mention. So if you ever need to sum up, let's say, every third term, you can do things like substitute in the roots of unity and sum up the results. So you could substitute in x as e to the 2i pi over 5, 4i pi over 5, 6i pi over 5, 8i pi over 5, and 1, and add those results, and you would get the sum of every fifth term. Now, depending on what exactly you're calculating, this may or may not be useful. Phew, okay, so that took a while. Let's move to question 15, which is a little bit more normal. Assume that ABC is an acute triangle with sine A plus B equals to 3/5 and sine A minus B equals to 1/5. If AB equals to 2022 root 6 minus 2, determine the floor of H, where H is the height of the triangle from C onto AB. Okay, so let's draw the triangle just as an acute triangle. It's AB, C is here, and this is your height. You may be thinking of a whole lot of clever ideas about solving for A, sine B, cosine B, but hang on for a second and let's think about what we really want to do. Because this question can be solved, but you don't really want to overdo it with a huge blast of trigo, because trust me, there's more trigo to come again soon. Now, because you know that sine A plus B and sine A minus B are super versatile, you can do lots of things with them. You can do sum to product, you can open them up, you can square them, you can do all kinds of things. And we're going to start with the diagram itself and see what we can conclude. Now, we are told AB and we want to find H. Now, how can we relate H to AB? Well, this height actually chops up AB into two smaller segments. You realize that if we call this point D, AD is H over tangent A, and DB is H over tangent B. Now let's just write this as cotangent, and that will make it a bit easier to write. So H cotangent A plus H cotangent B is equal to AB, which is 2022 square root 6 minus 2. I'm sorry about the occasional display messages. I think my internet connection is not that good here today. So the point of this is that H would just be AB, this 2022 root 6 minus 2, divided by cotangent A plus cotangent B. And so this tells you a very specific target. We want to target cotangent A plus cotangent B from the two given expressions. So let's write this down. Cotangent A plus cotangent B is cos A over sine A plus cos B over sine B. And why we convert it this way is because we know that these two expressions here, sine A plus B and sine A minus B, are full of sine A, sine B, cos A, cos B. So that is what we hope to see in our next couple of steps. If you combine this together, you get cos A sine B plus sine A cos B. Over sine A sine B. So you know that actually, wait a second, the one at the top is just sine A plus B. Which is 3/5. Meanwhile, the one below, we can use a product to sum to convert it back into A plus B and A minus B again. Right? It would be 1/2 cosine A minus B minus cosine A plus B. And both of these we know we can find. So as I said, I'm not going to go into all the technical details. I'm just going to give you the values. This is 3/5. Now take note that A plus B would be more than 90 degrees in an acute triangle. So therefore cosine will be negative. So cosine would be negative 4/5. And then sine A minus B is 1/5. Sorry, got cropped off. So that means cosine A minus B would be 2√6/5. Remember, I'm just using sine squared plus cosine squared equals to 1 throughout. Oof. Sorry, my computer is lagging a bit. Okay, and this 2√6/5, negative 4/5, and you see the √6 appearing down here, so we know that things are basically going well. I'll leave you to do all the simplifications, but after everything cancels off, you're going to get √6 minus 2 also cancelling off, and in fact this would just be a nice whole number even without the flaw. Okay, so I'll leave you to do the substitutions. Actually, √6 minus 2 will appear in the denominator, so this is not going to really take that long, as you would quite easily see. Okay, next up, question 16. Let A1, A2, and so on be a sequence if A1 equals to 1 and AN plus 1 equals to n plus 2 over n Sn for all n equals to 1, 2, and so on. So basically, your Sn is the sequence of partial sums, and they're defining each term in terms of the sum that you've gotten so far. Now don't think of this as the sequence is A1, A2, A3, and so on, and then Sn is just some other random attribute of the sequence. Think of it as there are two different sequences involved down here. Now Sn is the sequence of partial sums of An, but at the same time An is the sequence of differences of Sn. So what I'm going to do is this. I want to make my condition over here only involve either An or Sn. I don't want it to be a mixture. However, I think writing the whole thing on the right hand side as A1 plus A2 until An is not going to be the most productive way to do this. So I'm going to try to make both of them look like S something instead. And so I'll add Sn to both sides. Now Sn plus An plus 1 will be equal to n plus 2 over n Sn plus another Sn. Of course, the reason why we do this is that Sn plus An plus 1 is basically you add from A1 to An and then you add one more term, which is Sn plus 1. Whereas on the right hand side, both of them are Sn, so you can combine the fractions and it is going to be 2n plus 1 over n Sn. So that means that your sequence of partial sums is just going to multiply a fraction every time. And when you see n plus 1 over n and you keep multiplying that, you know that it's going to telescope. So let's write this down. Sn plus 1 therefore equals to 2n plus 1 over n Sn. And then the next one, after you apply one more time, would be 2n over n minus 1. Sn minus 1. And so on until you get down to S1. Now S1 is just 1 because it is just the first term. But you're going to collect a whole bunch of 2's, plus you're going to get a nice cancellation of your fractions. So this is equal to 2 to the power of n times n plus 1. So you just want to get pretty close to 2021 because S and A's are kind of close to each other. It's just a fraction n plus 2 over n apart, and n plus 2 over n is not a huge factor. So you try some power of 2 that is going to be big enough, and it will turn out that if you try n equals to 8, you get 2 to the power of 8 times 9. And this would be big enough. And you get 2304. So n equals to 7 will be much smaller than this because 2 to the 7 times 8 is a lot less. So if your n equals to 8, you get 2304. And that means that S9, remember n equals to 8 means S9, is this, and then an plus 1 is equal to n plus 2 over n Sn, so that means that a10 would be slightly bigger than this. It would be 11 over 9 S9, which is definitely bigger than 2021. Yeah, now you can also try n equals to 7, which is much smaller, and just verify it manually, but I'm just showing this to show that the numerical values are good enough. Yes, I see some of you mentioning brute force. Yes, if you try the first few values, right, and this is something I would probably do, you realize that it's growing really quick. So if it's growing that quickly, you are perfectly entitled to say, I don't care what is the pattern, I'm just going to write it until it passes 2021. And it will pass 2021 fairly quickly. In 10 terms specifically, it passes 2021. Okay, question 17. Each card of a stack of 101 cards has one side colored red and the other colored blue. Initially, all cards have the red side faced up and stacked in the deck, and then on each turn you take 8 cards at the top, flip them over and put them at the bottom. Determine the minimum number of turns required such that all the cards have the red sides facing up again. Now understand that there are two reasonable interpretations of this, which are both kind of possibly what is implied by the question. Now one interpretation is that you take the first 8 and then you flip all of them and put them at the bottom. So you take 1, 2 and flip them until 8. So I put prime to mean flipped over. Now some of you thought that no, we take the stack of 1 to 8 and we flip them over like this. And based on this, you will indeed get two different answers. The first interpretation of this, if you do this correctly, this interpretation of flip them over and place at the bottom would be 101. This interpretation of flip it over and place at the bottom would be 312. Now I have no official word on which is correct. As I said, this is not an official Math Society session, so I don't know which was the intended meaning of the problem. Because when you say take 8 cards and flip it over, whether you flip them one by one or you flip the whole stack, is not clearly implied. I would say though that the first one is easier. It's easier because there's quite a simple conceptual understanding of what is going on. So in the first understanding is the one that I'm going to focus on. I'm not going to talk so much about the second one, but if anyone is curious, just you can think about it, and there is quite a nice solution for that understanding too, just a bit longer. If you have this understanding of just flip the cards from 1 to 8 accordingly, what you would get is that you say that it flips like this, and then after you take the next 8, you flip it, and then you keep doing this. However, a potentially better way to think about it is not to think of putting it at the bottom. Now think of this as the 101 cards are all actually laid out in front of you in that order. And this kind of has a bit of allusions to computer science, where you are kind of moving a pointer through it instead of rearranging the whole list. So if you have a circular linked list, now for anyone that does a bit of programming, if you have a circular linked list, you might just move the head pointer by a few steps instead of really taking out the whole object and putting it at the back. So essentially, you start off at the top. Then you will flip the first 8, and I'm just going to tick it to mean it's been flipped once. And then after that, you're going to reach here. Now let's say that you then get to flip 9, 10, 11 until 16. Then you move the pointer after that. So you see that I'm now going to be at card number 17. I'm down here. Now after you do this, you're going to go until 101. So let's say after you made some moves and you have reached all the way to 96. Then you get to 97, 98, 99, 100, 101, and at this point you'll be back to card number 1. So you will continue like this. And then you will continue like this, and so on. Now what you need, in order for all of them to be facing up again, is that all of them should be flipped the same number of times, and that same number should be even. In other words, you need to flip every single card an even number of times as you're running through this. And since all of them you're just going in a loop, the difference will be at most 1, so it needs to actually be all the exact same number of flips. So therefore, the number of flips required has to be a multiple of 101. Notice I said number of flips. I haven't said the number of turns, but the number of flips is 8 times the number of turns. And so the only way that this can happen is if you just at least do it 101 times, which would give you 8 flips of every single card. So the minimum in this case would be 101. Now, as a hint for the other variation of this, where you may have thought that it was flipping the stack, what you can do is to actually group together 5 cards, then 3 cards. So you group together 1 to 5, and then you group together 6 to 8, and then you group together 9 to 13, and you just alternate 5, 3, 5, 3 throughout. And what you will notice is that those blocks of 5 and 3 never ever separate from each other. They kind of come in a group. So when this block of 5 is red, they're all red. When they're blue, they're all blue. And if you do this, essentially you're not going to have 101 cards. You're going to have 25 groups of 5, 3, 5, 3, 5, 3, 5, 3, and so on. So you can treat it as a stack of 25 cards, and you're just flipping 2 of them at a time. Okay, so that's just a mention to anyone that had this interpretation and was trying to solve that version of the problem during the SMO. Wow, so this has been taking a while. I think we'll do one more question and then we'll have another short break. Question 18 is actually a direct copy of last year's question 17, except with a couple of cosmetic changes. So it's almost Q17 from last year, which personally I don't really like that the question is almost reproduced exactly, but I suppose it does reward anyone that did read through the question and understand the approach. Now, in case any of you did not actually see that question from 2020, A, that's a bit unfortunate and you do have the right to be a bit aggrieved. But B, I'm still going to explain how we can approach this problem. Now we start with ABC being a triangle with AB equals to 10, and this rather odd looking condition, cosine A over cosine B equals to AC over BC equals to 4 over 3. If you see something like this, you can be a bit suspicious. This looks like it should be the sine rule, but it got replaced by cosines. So let's see what actually is happening here. Cosine A over cosine B and AC over BC, I'll just use the small side lengths B and A. By the sine rule, it's actually sine B over sine A. That looks suspicious. And when you see something like this, you should be fairly suspicious. In fact, you can then cross multiply. So sine A cos A equals to sine B cos B. And if you multiply 2 to both sides, it tells you that sine 2A equals to sine 2B. How can that be? Well, if sine 2A equals to sine 2B, it means one of two things, right? It either means that A and B are actually the same, or 2A and 2B could actually sum to 180 degrees, meaning A plus B is 90. Now A cannot be equal to B, because if A equals to B, the triangle is isosceles and the ratio would not have been 4 over 3. So therefore, it tells you that A plus B is 90 degrees, and this actually means that C is 90 degrees. So C is 90 degrees, and this is a right angled triangle. Now that this is a right angled triangle, you also see that the ratio is 4/3, so this is a 3-4-5 triangle. One of our favorite friends in geometry is the 3-4-5 triangle, and we get to see it here again. Of course, AB is 10, so it's not actually 3-4-5, it is 6-8-10, but close enough. Next thing, P is a point on the inscribed circle of triangle ABC, so you need to draw the incircle. So you draw the incircle. This is a bit annoying. You draw the incircle and you realize that you need to pick P from this circle. Now to pick P from this circle, there may be some geometric way of doing this, but to be honest, I don't really know of a very clean geometric argument for this. So I'm going to use a little bit of bashing, for one of a better word. So I want to know how to set up this in terms of coordinates. And to know how to set this up in terms of coordinates, I need to know the incenter. To know the incenter, I need to know the in radius. But you know that area equals to the in radius times the semi-perimeter. Area of this triangle is half times 6 times 8, which is 24. The semi-perimeter of this is 6 plus 8 plus 10 over 2, which is 12. So that means that the in radius is 2. And if the in radius is 2, that means that at least I know that I is 2. If I set C as my origin, and I'll just put the rest of my coordinates in. So now P can be anywhere on the circle, but I'm going to use the fact that it is a radius 2 and centered at 2, 2. I'm going to let P to be just 2 plus 2 cos theta and 2 plus 2 sine theta. This is your parametric form of your circle. Now if you work this out, you can find PA squared plus PB squared plus PC squared in terms of cosine theta and sine theta, which I hesitate a bit to write down in the remaining space that we have. So I'm just going to leave the computation out for this problem. Right? So you can find PA squared plus PB squared plus PC squared in terms of sine and cosine theta. And then from there, you would use the R formula to determine the optimal theta. I get a feeling I may have been missing something that is a lot easier to solve this question. So if there is, please share it in the chat. Yeah, so it will turn out that the optimal point P is just down here. Your optimal theta would actually be 90 degrees and P would be down here. Right, so I'll leave you to work out the details on your own, but once you have that point, obviously the distance is fairly straightforward. Right, so your maximum value would be 88. Okay, this is obviously not going to go keep within 2.5 hours, and I do want to explain each of these questions to a reasonable amount of detail. Right, so let's again take a quick break for 5 minutes or so, and then when we are back, we'll look at the last 7 questions. Okay, welcome back everyone. If you have just joined, I left out the message on screen for a short while. This entire live stream will remain up on YouTube in case you want to see some of the earlier questions which you may have missed, or if there was something you just wanted to write down that you didn't quite pick up during the live discussion, you can always watch it back again. Okay, so we have got 7 questions left, and we are obviously not going to finish by 5:30, but we'll try our best to wrap this up at a reasonable time. I know when on AOPS, when they do math jams, to go through the questions after the AIME, the 15 questions takes about 3.5 hours. So we have 25 questions here. I think it is quite difficult to finish it in that little time for an SMO Open, but we'll try to keep it prompt. Alright, for question 19, a basket contains 19 apples labeled by the numbers 2 to 20 and 19 bananas labeled by the numbers 2 to 20. Right, so Abeng picks M apples and N bananas from the basket, and he needs to ensure that for any apple labeled A and banana labeled B that he picks, A and B are relatively prime. This is a very strange way to pick apples and bananas, but he's trying to get the largest possible value of M times N. Right, so M and N are the number of apples and bananas. Okay, you need to find a suitable equivalent condition for relatively prime so that we don't have to just go and try out, okay, what happens if he picks apple number 2? What happens if he picks apples number 7? And what happens if he picks banana number 12? Right? This is not going to be a very efficient way to go about things. One way you can think about relatively prime is to think about it in terms of prime factors. You must have A and B do not share any prime factors. That's what it means to be relatively prime. So they don't share any prime factor, and this is true for any apple and any banana. And so actually, this means that you can think of it in the following way. If any apple and any banana, their numbers don't share primes, it means that there are a set of primes that are exclusive to the apple collection, and there are a set of primes that are exclusive to the banana collection. And then your prime factors of 2, 3, 5, 7, 11, 13, 17, and 19 kind of have 2 choices. You just send them either to A or B, and based on those prime factors that you select, you can pick as many as you want that are formed only using those prime factors. So for example, if you put 2 and 3 under apples, that means that 2 is allowed, 2 squared is allowed, 3 squared is allowed, 2 times 3 is allowed, 2 times 3 squared is allowed, and so on. And so you need to decide on the best possible partition of your prime numbers. Now we can further say that actually the 11, 13, 17 and 19 only do one thing. They're just themselves, right? There's no other multiple of 11, 13, 17 or 19 other than themselves. And even for 7, there are only 2 multiples, 7 and 14. So most of the decision making comes from where you put the 2, 3 and 5. So I'm going to just partition it like that. So most of the decision making comes from where you put 2, 3 and 5. Okay. So let's write down a few cases and we'll see which is the best. Now without loss of generality, you can assume that 2 comes here. Since if you just flip it around, there's no difference. So I only need to consider cases on 3 and 5. So let's say that you put 2 here, and then you pass 3 and 5 to the other side. Now what does that give? 2 gives you 2, 4, 8, 16. And then 3 and 5 would give you 3, 5, and then 3 squared, which is 9, and 3 times 5, which is 15. Now then, in that case, 7 you would rather put it on the left since that contributes plus 2, which is 7 and 14. Whereas on the right, it only contributes 7. So you put 7 down here. That would give you 7 and 14. And then you have got the last four numbers, 11, 13, 17, and 19. So as we know, when you want to make a product as big as possible, you want to make the two numbers equal. So the best you can do is put 3 more numbers here, 3 of your 4 floaters, so to speak, which you can assign to either side without affecting anything. So you can put 3 here and you put 1 here, and then you get 7 times 7, which is 49. So this is the first case, if you put 3 and 5 on the other side. And now the next case would be if you put 2 and 3 together, but 5 on the other side. And 2 and 3 together does a lot for you. And 2 and 3 basically gives you 2, 4, 8, 16. And then 3, 6, and 12. And then 9 and 18. So this already has 9 numbers down here, whereas 5 is just itself. Now here you can choose to put 7 on the left or the right. If you put 7 on the left, that would give you 2 more. If you put 7 on the right, that would give you 1 more. Now, you would see that among these two, the best option is because the one on the right is really short of numbers. So the best option that you could do would be to put 7 down here, and then to also put all the 4 more prime numbers down here. You put all the prime numbers down here, and this time it would be 9 times 6, which is 54. Now that is still not the optimum. There are 2 more cases which you should consider, whether you put 2 and 5 together or you put 2, 3, and 5 together. So I'm going to skip one of the cases, which you can also do on your own, which is, so I'll skip the case where you put 2, 5 on one side and 3, 7 on the other side, and we're just going to look at 2, 3, 5 all on the same side. Now if 2, 3, and 5 on the same side, you get a real glut of numbers available to you down here already. Right, so apart from this whole block of numbers, so you get all of these, which I shall move to fit into the screen. You also get 5, 10, 15, and 20. Because that's what you can get just using 5. Now it's fairly clear then that you should put everything else on the other side so that you can maximize the product. So you just put the other 5 there, 7, 11, 13, 17, and 19. And then this would give you 13 times 5, which is 65. And 65 turns out to be the optimal configuration. So it turns out to be the largest possible value from this optimal configuration. Okay, so that's for question 19. Next up, question 20. Let px equals to ax squared minus bx plus c be a polynomial where a, b, c are positive integers and px has 2 distinct roots in the interval 0, 1. Determine the least possible value of a, b, c. Okay, so some of our intuitions may be to use Vietas immediately and to say that maybe I should write alpha plus beta equals to b over a, and alpha beta equals to c over a. Now, if you had this intuition, that's not a bad starting point. However, we realize that we don't have much to go on in terms of what alpha and beta should be, because alpha and beta may not even be rational. Right? You may actually want to have irrational roots that somehow give you nice, simple fractions b over a and c over a. And that means that it may not be such a good idea to use Vietas in this case. In fact, we're going to use a lot more of a low-tech approach. We're just going to use the discriminant and the quadratic formula. And it's a very, very low-tech, but it works. So the first thing is that it has two distinct roots in an interval 0, 1, which means there are at least two real roots. And so the discriminant, which is b squared, is happening to my... Okay, sorry, give me a second. B squared minus 4ac must be greater than 0. Now the other thing that we can do is to say that the roots must be between 0 and 1. So let's write it down from the quadratic formula. Your roots are b. Now remember, this is negative here, so it's positive b, plus or minus the square root of b squared minus 4ac over 2a. This is in the interval from 0 to 1. Now, assuming that the discriminant condition is true, so if this is positive, it will still be less than b, so it's less than b squared, which would mean that both of the roots will be positive for sure. Right? Because the second square root is less than b, so this would definitely be more than 0. So that's not the part you need to worry about. What you need to worry about is the positive root must be less than 1. So that's what we need. Now if you move this over and rearrange, you get root of b squared minus 4ac is less than 2a minus b. You can square it and simplify. It turns out to be pretty good. So when you are about to square it, you see that b squared is going to cancel out. So therefore this is not such a bad idea. So you can divide everything by 4a, and the implication after you simplify is that b is less than a plus c. Okay, so that's your second condition, and those two conditions guarantee that your two distinct roots are between 0 and 1. Okay, so what do we do with these two conditions to find the least possible value of a, b, c? Honestly, not that much. We just need to make sure that a, b, and c are quite small. We would imagine that there should be some small values of a, b, and c that do satisfy this. So how might we approach this problem? You can just see that since b is less than a plus c, the smallest possible combination would be if a plus c is 1 and b. In other words, your 4ac is at least going to be b. So if you combine that, it means that b squared is greater than or equals to, b squared is greater than 4ac, which is itself at least 4b. So if b squared is greater than 4b, that means b must be at least 5. And certainly you want b to be as small as possible, because if b is as small as possible, then your a and c can also be small while satisfying the second condition. And so we can let a equals to 5 and b equals to 1. And take note that down here, you also need to make sure that this is positive. There was actually one more condition that I didn't mention immediately. If this is negative, then that's already not going to give you something greater than the square root. So this must be also greater than 0. And that tells you that you can't actually put it in the opposite direction. It can't be 1 and 5, it must be 5 and 1. So 5 and 1 will satisfy everything, and so ABC is 25. Okay, next up, question 21. Now, normally, if you have such a question, I would tell my students or anyone that angle A should be quite nice. It probably is either 120 degrees, 135 degrees, or 150 degrees. And unfortunately, this is one of the exceptional cases where that is not true. To start with, let's try to draw a decent looking diagram to understand how this would look like. Now, you won't be able to draw a perfect diagram because you don't know the size of angle A, right? So don't expect your diagram will look perfect, it just needs to look decent enough that you know what's happening. Try to draw the circle first when drawing a diagram so that it is at least possible to make your tangent lines look vaguely like tangent lines. Now you have the benefit of being able to do this with a ruler. I'm doing this freehand and hopefully it is passable. So let's call this C, A and B. And then it touches the sides at 2 points, A1 and B1. Now the line A1, B1 meets the extension of BA at X such that CXB is 90 degrees. So if you extend this, they intersect, and they intersect at a 90-degree angle. Oops, okay, let's draw a giant point. And let's make that look a bit more straight looking. Now remember, we didn't actually know what angle A should be, so there was no reason why this would actually turn out to be perfectly straight. Right, but for our sanity's sake, let's try to make sure it looks decently straight. Okay, and this point is X. Now we're given a rather strange looking condition. BC squared equals to AB squared plus BC times AC. Let's write it using the small side lengths as A squared equals to C squared plus AB. And you're asked to find angle A. From this, basically two conditions are involved here. The first condition is that this green dotted line here is actually a straight line. X, B1, A1 are collinear. And the other condition is this strange looking algebraic one. Now, if you do know something special about, let's say, this configuration, let's say you know something significant about a1, b1, and x being collinear, then you probably want to start with the geometric ideas first. You start off by exploring what does that imply, and then later you figure out what's the use of the algebra. But more often than not, you probably have no idea what is so important about this configuration, and what's so special about it. And in such a case, it's maybe better to look at this figure and say, forget it, I'm just going to work with the algebra first and see what it tells me. Alluding to pattern recognition again, this thing looks vaguely like the cosine rule. Now, it looks vaguely like the cosine rule, but with a couple of things missing. So let's write down the cosine rule and try to combine them to get something useful. Now, the cosine rule, you might ask, which one of the three so-called configurations? Well, you want to know the size of angle A, right? So let's use the one with angle A. So the cosine rule, A squared equals to B squared plus C squared minus 2BC cosine A. It seems like a decent choice. And now I'm going to substitute them in, or you can say subtract the equations, whatever it is. But if you combine them, so you just equate the two right hand sides and cancel off C squared. B squared minus 2BC cosine A is equal to AB. And you can rearrange this to isolate cosine A, divide by B throughout, and you would get B minus A over C equals to 2 cosine A. Now, when you get a very simple looking condition like this, when I say simple looking, meaning that it doesn't have that many interplays between A, B, and C, this is just B minus A over C equals to 2 cosine A, it probably means something nice. But unless you have seen an immense number of geometry problems, you may not know what is the significance of this condition either. So let's play around with it. And when I say we play around with it, it must mean something useful. But if we don't know what it is, let's keep on molding it until it gives something that we can concretely work with. So first of all, there's a weird mix of side lengths and cosines. I'm going to use the sine rule to make it look only like sines. So B over C is sine B over sine C, A over C is sine A over sine C, so we have this. I'll move sine C over. And you get this rather enticing looking 2 cosine A sine C. It looks really enticing and juicy, like one of our product to sum identities. So let's do that. Let's use the identity. Now the identity will tell us that it is sine A plus C minus sine A minus C. Okay, wait a second. In a triangle ABC, A plus C is 180 minus B. So this is actually equal to sine B. And so these two turn out to be the same. And therefore we concluded that sine A equals to sine A minus C. Obviously, sine A equals to sine A minus C. It doesn't mean A is equal to A minus C. What it means is that these two sum to 180 degrees. So therefore, 2A minus C, which is the sum, equals to 180 degrees. And we can write C as 2A minus 180 degrees. So that's the very, very interesting but strange looking conclusion that we got from working through all of this. Okay, but we have found angle C in terms of angle A. So hey, we are one step closer to solving the question since we are supposed to find angle A, and we have found one other angle in terms of angle A. Alright, now let me grab this diagram and carry on with this condition. So we've got this diagram over here, and we have got the condition just shown that C is equal to 2a minus 180 degrees. So let's see if we can angle trace anything out of this. Now if C is 2a minus 180 degrees, I can look at it and see that, okay, CA1, B1 is isosceles because these are common tangents. And so that means that this angle is 180 minus C over 2, which is, interestingly enough, 180 degrees minus A. And so therefore this angle is actually equal to angle A as well. Now if that angle is equal to angle A, it implies that we have a pair of similar triangles. Triangle XA1B is similar to triangle CAB. And the interesting thing that you get out of that is the third angle. The third angle is over here. So angle A1XB equals to angle ACB. So if these two are equal, then we get a cyclic quadrilateral. So A1, CX are concyclic. Since they are concyclic, it means that one of these is a right angle. So CA1A is also a right angle. Now look at that carefully. CA1A is a right angle. However, normally CA1 should be perpendicular to the radius of the circle, right? The in radius. So CA1 is supposed to be perpendicular to A1I, where I is the in center. And so that means that AI, A1 are collinear. And you know that AI is the angle bisector. So that means that AA1 is also an angle bisector. But it is an angle bisector that also gives you a right angle. So that means that the triangle is isosceles. After all that, that's the conclusion. So our conclusion turns out to be that, hey, this triangle is isosceles, so therefore this is also the same. If we combine this together and solve, it tells you that based on your angle sum, A is 108 degrees. So I found it interesting that the whole paper didn't really have much of an application of cyclic quadrilaterals and of this classic geometric stuff. I guess it was pushed all the way to the back. Phew. Okay, question 22. Find the number of positive integers n such that 7n minus 16 divides n times 13 to the power of 2019. Okay, so what do we do with something like this? Now, intuitively, you would want to try to do some sort of a long division. But to do any sort of a long division, you need 13 to the power of 2019 divided by 7, which is fairly hopeless. So how can we avoid doing that? Well, there's one way to simplify it, which is that this is equivalent to if 7n minus 16 divides 7 times of n times 13 to the 2019. The reason why we can introduce the factor of 7 is because clearly this does not have a factor of 7. So since 7 does not divide it, if we introduce 7 to the right hand side, nothing will go wrong. So now we can kind of do a long division. I'm just going to write it out without the division by writing it as 7n minus 16 times 13 to the 2019 plus 16 times 13 to the 2019, which means that you've reduced it to 7n minus 16 must be a factor of 16, let's write it as 2 to the power of 4 times 13 to the power of 2019. Okay, so we have done our first part of our objective, which is to now rewrite it such that the dividend, so to speak, is just a constant. And it's a constant that is still in prime factorized form. So things are going well so far. Now what you want though, is not just all the factors of 2 to the power of 4 times 13 to the power of 2019. What you want is factors of the form 7n minus 16. Now what are the numbers in the form 7n minus 16? Well, for small n, n equals to 1 is minus 9, then minus 2, and then 5, 12, 19 and so on. So for all the positive values here, these are just anything that is 5 modulo 7. Meanwhile, minus 2 is going to be a factor of this, minus 9 is not. So let's not forget these two. My condolences if anyone missed out n equals to 2 as a possible solution to this. Now, so apart from minus 2, the rest of them are positive factors which are 5 modulo 7, and you're just hoping to look for how many factors that are 5 modulo 7 are there of this number. Now, in order to count the number of 5 modulo 7 factors, we can use the same idea as we did when we want to count the number of factors in general. We just decide what power of 2 is appropriate and what power on 13 is appropriate. So the factor, let's say factors would look like 2 to the power of A times 13 to the power of B. And for 2 to the power of A, if A is 0, then this is 1. A equals to 1, it is 2. A equals to 2, it is 4. For A equals to 3, it is 1 mod 7 again. And then for A equals to 4, it's back to 2. Meanwhile, for powers of 13, 13 is actually negative 1 mod 7. So it's just going to alternate between 1, minus 1, 1, and so on. Now, how do you get 5 mod 7? Well, there's no 5 in the left column, so we can't use 1 times anything. But we can get it from 2 times negative 1. So 2 times negative 1 is negative 2, which is 5 mod 7. So out of these, there are 2 possible A's, A equals to 1 or 4. And on this side, B can be anything odd, which is 1 mod 2. So anything odd will work out, and out of B from 0 to 2019, exactly half of them are going to be odd. So therefore, the number of factors first, you have to take 1 from this negative 2, don't forget about that. And then you have 2 times of 10, 10, which is half of them. And finally, at question 22, we get our belated appearance of the answer 2021. Okay, next up, question 23. So in the acute triangle ABC, P is a point on AB, Q is a point on AC such that BP plus CQ equals to PQ. The bisector of angle A meets the circumcircle of the triangle ABC at the point R distinct from A. Okay, so that means that we should start by drawing the circle first. Draw a decent looking circle. If you are like me, which I have a lot of difficulty drawing a nice looking circle on paper, use a compass just to make sure that your diagram is somewhat in order. I'm just going to put ABC somewhere on it. I'm not sure where they should be just yet. I know this looks a little bit equilateral, but let's just put ABC down first, somewhere. So P is somewhere on AB and Q is somewhere on AC such that BP plus CQ equals to PQ. Okay, so let's try to make that look somewhat believable. Somewhere here, let's say. And then R is the point where the circumcircle of the triangle meets the angle bisector of A. So I'm going to draw that in. And this is R. Now suppose that angle PRQ equals to 52.5 degrees. Find the value of angle A. So let's mark this out first. Now the first thing that you should take note of is a very common property when you have an angle bisector and you draw it onto the circumcircle. If you have an angle bisector and you draw it onto the circumcircle, then because of your angles in the same segment, it means that this would move over here and over here as well. In other words, BR and RC are equal. It's an isosceles triangle. And the point R is at the midpoint of the arc. Now, AR is actually not very important anymore since we have already noted this down, so I'm going to erase it off. So for the time being, I'm going to erase it off. Oops. What's the other important thing they told me? They told me that BP plus CQ equals to PQ. You have to figure out what's the use of that. Well, since BP, PQ and CQ are all kind of linked together, a very natural construction would be to put the point down here. Let's call this point X. It's a natural construction to put it there such that these two are equal and these two are equal as well. Because by doing that, you have essentially made use of the condition already. So you have made use of the condition and you've gotten yourself two isosceles triangles, which I guess I shall draw in. Okay, so what comes next? We have to make use of all of these isosceles triangles in some way, and we care very much about the angle A. Right, so I'm going to do some angle tracing down here. Now first of all, angle A is over here. If I wanted to see there are two isosceles triangles that are kind of adjoined to it, I can get their total angles first. So angle BPQ plus angle CQP, just using exterior angles and nothing else, on triangle APQ, it would be 180 degrees plus A. Now that means that the two pairs of equal angles sum to 180 degrees minus A. And so if I take PXB plus QXC, that would be half of what I just said. So that would be 90 degrees minus A over 2. And in turn, that means that angle BXC is equal to 90 degrees plus A over 2. Now there's something interesting here that happens. Because this is 90 degrees plus A over 2, you probably ask yourself, maybe what's so important about that? But you see that you have this point R over here, which hasn't played any role. Now, what angle is this? So this big angle is 180 degrees minus A in your circle. Which means that if you were to actually take the reflex angle around it, this reflex angle is 180 degrees plus A, which is 2 times of angle BXC. Now, so it's 2 times the angle BXC, and you know that RB equals to RC. So the conclusion is that R is actually the circumcenter of BXC. And if R is the circumcenter, the point of that is that you get a couple more isosceles triangles. So Rx is also equal to the other stuff. But then that means that if we have marked this stuff out, we just get a couple of congruent triangles. So B is just the reflection of X over PR, and C is just the reflection of X over QR. Which means that we can mark out a couple more equal angles that are pretty important to us. We can mark out that these two angles are equal. And we can mark that these two angles are equal. So therefore, having marked out those pair of angles, angle BRC is going to be 2 times of PRQ, which is 105 degrees. And finally, angle A is 180 minus this. I think the key to this question is to construct the point X and to make use of these two isosceles triangles, because without that, the condition BP plus CQ equals to PQ is not the most useful thing in an algebraic sense. Okay, 2 more and we'll be done with this. And question 24 is the thing that some of you have been clamoring about a bit. Now indeed, this is none other than your Gaussian integral. It is what comes from your normal distribution. So let me mention first that this comes from your normal probability density function. So the normal PDF given mean, mu, and variance sigma squared will be 1 over 2 pi square root sigma e to the power of negative x minus mu squared over sigma squared. Now if you look at this here, you can tell that it is essentially in the same, oops, I forgot 2, yes. It is essentially in the same form, with the very important exception that there's a whole bunch of constants everywhere. However, the property that we have for a normal distribution and any probability distribution is that the area underneath it is 1. So if you let mu equals to 0 and sigma equals to 1, then your density function would just be 1 over 2 pi e to the negative x squared over 2. Yeah, so I see a comment on question 23. Yes, I think you can construct another congruent triangle to obtain this same result. I guess that was the construction that came a bit more naturally to me, but constructing a congruent triangle to obtain this would certainly have worked out pretty well too. Okay, so anyway, back to here. The implication of this is that if you take the integral of something like this, a probability density function from negative infinity to infinity, it should be 1. And so S is just 2 pi times of this. Sorry. Oh, oops, I think I got this inverted, right? Sorry. Square root 2 pi sigma. Yeah, this is a bit annoying. So we square root 2 pi times of this. Which is just square root 2 pi. And so your answer becomes just the floor of 2 pi, which is 6. Now, for the benefit of anyone that is still here, and thank you for sticking around, by the way, S squared can also be done using a double integral. So how do you actually find out this value without having known Gaussian integrals? Unfortunately, it means you need to know a little bit of multivariable calculus. Not sure if you can suggest any alternative. So S squared, you can write it as this integral squared, but I'm going to use two different variables for the integral. And then we can combine these two integrals together into a double integral. Of e to the negative 1/2 x squared plus y squared dx dy. Essentially, S squared now becomes the volume under a quite strange looking shape. At this point, you can do a substitution into polar coordinates. So r equals to square root x squared plus y squared, and your theta is the usual one for polar coordinates. So I'm not going to write theta down. The more important one, since we are using it for dx dy, is that dx dy equals to r dr d theta. So this is the way of changing your integration variables from x and y to r and theta. And we didn't need to mention theta as tangent inverse of y over x here because it doesn't appear anywhere. You just can work with r and theta. So instead of integrating from negative infinity to infinity in both the x and y directions, we can change it around into integrating as theta goes from 0 to 2 pi, which is a full revolution, and r goes from 0 to infinity. And this would be e to the negative 1/2 r squared and r dr d theta. So I'm just thinking of explaining how this all works. It's not that you would be expected to do this, because this is something that you probably see in your first university course on statistics rather than in the SMO context. But nonetheless, I think since you are here and you have been told that the integral is just 2 pi, you may ask why. Okay. Now at this point, the inner term here, you can use substitution. It just becomes negative e to the minus half r squared. And then by the chain rule, you get r coming out. Yeah. Some of you are a little bit bothered about why is there this in the SMO. I'm also a bit curious about it. Why did this pop up this year? But technically, calculus is not part of the scope of the IMO. Right? So for a long time, there's no calculus. And then suddenly, calculus showed up. And once calculus shows up, there's no real clear-cut definition of what is acceptable calculus and what is unacceptable calculus. No one really ever said anything about that. So I think there isn't much grounds to complain, unfortunately. Yeah. Anyway, this integral, the limit as equals to infinity is 0. So the only thing that applies is when you put in 0. So you get integral of 0 to 2 pi of 1 d theta, and this is equal to 2 pi. So I think doing this sort of a double integral, maybe only some of you doing further math or having done a little bit of multivariable calculus in some other context, maybe for physics, you'll be comfortable with this. Right? But this is not the most typical transformation, and certainly it's not something you would think about on the spot if you've never seen it before. So I just thought I would mention the derivation of how is it that s squared actually turns out to become 2 pi. Okay, fairly out of breath, but we have one question left, which is 25. And thankfully, it is not actually that bad. So you have two sequences an and bn. A1 is p, b1 is q, and you have these two recurrence relations. You're supposed to find a rather strange looking limit, but that rather strange looking limit, I think we can start by just understanding our two strange looking sequences first. An is, well, actually not that strange. It's just p to the power of n, because you just keep multiplying by p every time. So a1 would be p, a2 would be p squared, a3 would be p cubed, and so on. So that's not very complicated. Let's try to look at the sequence bn. Now b1 is q, b2, you take q times of a1 plus r times of b1. So it is pq plus qr. Now b3, you take q times of a2. So qp squared. And then r times of b2, which is pqr plus qr squared. Now I notice that there's a common factor of q that keeps appearing. This is qp plus r. This is qp squared plus pr plus r squared. Let's maybe write one more down, and just to confirm that such a thing does happen. And whatever patterns we observe, we could always prove by induction, although that's not an SMO requirement to say the least. Okay, so this one would be qp cubed plus qp squared r plus pqr squared plus qr cubed. And you see that the same thing holds. It is q times basically all of the different degree 3 combinations of p and r. Now these can be combined together. For example, if you have p squared plus pr plus r squared, you know that this is q times p cubed minus r cubed. Oops. P cubed minus r cubed over p minus r. Towards the end of every session, my stylus starts malfunctioning. Probably too much writing. For this one, it would be p to the 4 minus r to the 4 over p minus r. And conveniently enough, that's something we see here. P minus r equals to 4q. So for example, in the last one, it would just become 1/4 p to the 4 minus r to the 4. Okay, so it should be quite clear what the pattern is and what the general term is like. An is just p to the n, and Bn becomes 1/4 p to the n minus r to the n. Now let's look at the limit we are supposed to find. The limit that we are supposed to find, there's a square root at the top and Bn below, but we can actually combine it in together. That will be easier to evaluate. So if we bring it in, it becomes An over Bn squared plus 9. And since p is greater than r, the r to the n is going to be insignificant as n goes to infinity. An over Bn is just going to tend to 4 because you have p to the n here and you have 1/4 p to the n here. So therefore, this limit is just going to be the square root of 4 squared plus 9, and that is equal to 5. So finally we are done. It took us about 3 hours, although that's with a bit more explanation than one would expect if you were doing it as a participant rather than explaining everything in detail. So many thanks to everyone that has sat in through this whole time. I don't imagine that all of you who are watching now were here at the very start. But thanks anyway, and you can always look back at the start of the stream if you missed the earlier questions. Now, one thing I want to say is that the SMO Open obviously is not very easy, but there's kind of two different zones of it, right? There are the questions which are doable with some practice, and then there are the questions that need quite a lot of ingenuity. So depending on where you're at, currently, you would be targeting something different. So don't be either too frustrated by the impossible looking questions or just dismiss everything as trivial at the start. Right? Just find a healthy balance of what is a good target for yourself, and try to always take a next step up to a more difficult type of problem each time when you encounter such a contest. So thanks everyone for joining again, and as I said earlier, a bit of self-promotion. If you liked this session, you benefited in some way, please like the video, subscribe to the channel, and give any comments below after the session if you found that there's a better solution you thought of for any question. So please have a good rest and a good dinner, and hopefully I'll see some of you guys around again. Alright, so I'm going to go off camera now. I'll leave the chat on for a short while in case any of you have questions or you want to just talk about air some of your grievances or discuss some of your scores or cutoffs or whatever, and then I'll probably close this in about 5 to 10 minutes time.